All right, today we're diving into something that sounds like it's straight out of a sci-fi movie. We're talking about creating cold, not with chemicals, not with big compressors, but with pure sound. It's this quiet revolution that could totally change how we cool, well, everything. So let's just start with that big, kind of mind-bending question. How in the world can you use a sound wave, just vibrations and energy, to actually pull heat out of something and make it cold? It seems impossible, right? Well, that's exactly what we're going to break down. But first, you might be asking, why do we even need a new way to do this? The answer is pretty stark. Our current cooling methods are a massive part of the climate problem. It's a tough irony, isn't it? The very machines we rely on to stay cool are making the whole planet hotter. Okay, so let's dig into that. Section 1, our refrigeration problem. The issue here isn't just about the electricity these things guzzle down. It's about what's humming away inside them. We've got a major problem with the powerful chemicals that make it all work. Yeah, the bad guys here are these chemicals called hydrofluorocarbons, HFCs for short. And these things are no joke. They are incredibly potent greenhouse gases. We're talking hundreds, sometimes thousands of times more powerful than CO2. Now, the good news is the world has woken up to this, and there are international deals in place to phase them out. But that means the race is on to find a replacement, and fast. And that replacement, well, it might just be one of the most elegant and surprising solutions you could imagine. Instead of messing with more complex chemicals, we can turn to the basic physics of sound. This whole field has a name: thermoacoustics. At its heart, thermoacoustic cooling really is just this. It's a process where you use a really powerful, finely tuned sound wave to literally pick up heat energy from one spot and dump it in another. One side gets cold, the other gets hot. And the best part? No nasty gas is needed. So how on earth does this actually work? How can a wave of pressure start messing with temperature? To get it, we need to understand two really basic principles of physics that, when you put them together, create this amazing effect. First off, let's just remember what a sound wave really is. It's not just noise, right? It's a physical wave of high pressure and low pressure moving through a gas, like air. You get these spots where molecules are all bunched together, that's high pressure, and spots where they're spread out, low pressure. And this is just such a cool way to see it. You can literally make the invisible visible. If you put tiny little styrofoam beads in a tube and blast a specific sound frequency through it, those beads get pushed around by the pressure waves, and they all collect in the high pressure zones. It's an amazing way to actually see the structure of a sound wave. Okay, now here's the second piece of the puzzle, and this is the absolute key to the whole thing. It's a fundamental law of physics. If you take some gas and you squeeze it really fast, you're cramming all its energy into a smaller space, and its temperature just shoots up. And guess what? The high-pressure parts of a sound wave are doing exactly that hundreds of times every second. And we actually see this powerful idea in other places. A fire piston is a perfect example. You slam a plunger down, compress the air so fast, it gets hot enough to light a piece of cotton on fire. A diesel engine does the same thing. It uses insane compression to ignite fuel, no spark plug needed. A sound wave is just doing this on a tiny, super fast scale, but the physics is identical. So we've got our two main ingredients. Sound creates pressure, and pressure creates heat. Now let's put them together. How do you actually engineer these ideas into a machine that can make things cold whenever you want? It all comes down to this really clever four-step cycle. Let's walk through it. First, boom, a powerful sound wave compresses a little packet of gas, making it hot. Second, right as it gets hot, it moves through this special spongy material called a stack. This thing is designed to just suck the heat right out of that hot gas. Third, the sound wave passes, the pressure drops, and that same gas expands. But here's the trick. Since it already lost its heat, it gets way colder than it was to begin with. And finally, that super cold gas flows back across the other side of the stack, and now it absorbs heat, creating your cold spot. This whole dance repeats hundreds of times a second, just constantly pumping heat from one end to the other. And get this is not just some theory on a whiteboard. On the left, sure, you see the technical drawing of how it all fits together, but on the right, that's a real deal ice cream freezer made for Ben & Jerry's that uses this exact tech. It keeps the ice cream frozen solid with less energy and way less noise. This proves that thermoacoustics is already out of the lab and in the real world. And that brings us to our next section, a multi-billion-dollar future. The point here is that this is way more than just a neat science experiment. This technology is getting ready to become a huge industry, all because we desperately need new ways to cool things down sustainably. I mean, just look at the numbers. Market forecasts are saying that the global market for these thermoacoustic cooling gadgets is going to hit over $3 billion by 2033. This isn't some niche idea anymore. This is becoming a serious economic force. And this chart really just drives that point home. We are looking at the market more than doubling in less than a decade. That shows a crazy amount of demand and a ton of confidence that this is a real, mainstream solution for the future. So where is all that demand coming from? Pretty much everywhere. We're talking about cooling powerful computer chips and the batteries in electric vehicles. It's being looked at for aerospace, where things have to be super reliable. It's perfect for sensitive medical devices that can't have any vibrations. And of course, for keeping our food fresh. The fact that it can be used in so many different ways is one of its biggest selling points. And here's where the vision gets really big. Some of these thermoacoustic engines can be powered directly by a heat source. Think concentrated solar power. So you can start to imagine a future where whole communities could have sustainable air conditioning and refrigeration, running off the sun with almost no moving parts and a tiny carbon footprint. But believe it or not, the story doesn't even stop there. As incredible as all that is, researchers are now pushing the science into a completely new territory, one that could lead to devices that are even simpler and more mind-blowing. That's right. People are now proving that you can create the same thermoacoustic effect inside solid materials, like a metal rod. Just try to picture that, a fridge with no gas, no liquid, and zero moving parts. Just a solid bar that gets cold on one end when you apply the right vibrations to it. Which leaves us with this one last amazing thought. We started this journey talking about our noisy, complex machines filled with planet-heating chemicals, and we've arrived at a solution that uses sound itself to create cold, with no harmful gases and maybe one day, not a single moving part. So you have to wonder, could the future of cooling not just be clean, but completely, totally silent?